Hiya, welcome to the session on developing the future of transport. I'm just waiting for one final speaker to come, but then we'll go ahead and get started. I hope everyone's been enjoying 6Ed. Certainly been an interesting conference this year, and I've certainly been enjoying the different presentations. In this particular session, if you have questions, please feel free to enter those via the moderations board. We'll be able to respond in that way. The speakers will each talk for about 15 minutes, but we're really hoping that this will largely be an opportunity to discuss kind of emerging needs and expectations and places where we need quite a bit of interdisciplinarity in transport. It's an exciting area, and I'm certainly excited to hear what the speakers have to say. So I'm Caitlin Cottrell. I'm Director of the Center for Transport Research at the University of Aberdeen. If I can just get my PowerPoint to move. Intelligent transport is seeing significant growth at the moment, whether it comes to connected and autonomous vehicles, which are things that we're seeing quite a bit about in the news, but also into things such as journey planners, and the real-time public transport information. The integration of technology and transport is reaching a critical area, but it's also implying significant challenges. Things such as accountability, which I'll give a plug for a project that we have running here, which is realizing the accountable intelligent systems, but also issues such as cybersecurity and privacy. These are all really things that are impacting upon our access to technology, our use of technology in the transport sector, and it also has impacts for how comfortable people feel with using some of these technologies. And it also requires a really wide variety of skills that perhaps some of which have been traditionally seen within the transport realm, others of which we don't necessarily have as much experience with. So things like modeling and simulation, machine learning, data mining, these are all really critical to a number of transport applications that are coming out at the moment and that we're seeing quite a bit of need for in the near future. And that's really evident in what we're seeing within the marketplace and in the jobs market. So joint research between the Transport Systems Catapult and Deloitte has indicated that the intelligent mobility sector could be worth about £1.4 trillion globally by 2030. So it's not a minor thing, and certainly we're seeing applications at the moment largely within freight and logistics, particularly in the wake of the pandemic, but also just expectations moving forward. And to take advantage of this growth, the UK needs to invest not only in infrastructure, but more critically in the skills. And it requires input from kind of traditional transport people, so planners, civil and structural engineers, but also critically from data and computing scientists. And this is really an area where we see a significant need and significant opportunity. So to give us a little more input and information on that, we have three speakers today. Dr. Rick Sarkar from the University of Edinburgh, Mr. Saeed Mehdi from the University of Glasgow, and Dr. Patricia Franco from the Connected Places Catapult. They'll each talk for about 15 minutes. Again, if you have any questions, feel free to put those in the discussion board and I'll have access to those. And what we're hoping is really to utilize the presentations as a springboard for future discussion about emerging needs. So with that, I will pass it over to Rick.
Thank you, Caitlin. Let me just start my screen sharing here. Okay. Right, so you can see the screen, right? Okay. So I'm going to be talking about some challenges in machine learning for mobility and transport. Well, there are many challenges. I'm going to be talking about only a few of them today. And we will also speak about a little bit of work we have done on them. So let's see. One challenge is that in this sort of when you talk about transport, say in a city, there are many people involved, complex movement, lots of data, lots of vehicles. And if you think about it, each person's phone records GPS data all the time, potentially. At least many people's phones do. And in principle, we can make use of all of that data to substantially improve our transport systems and help people move better. But the problem is that this huge amount of data requires huge computational resources. The second problem is that this complex movements. So people move in complicated ways. The trajectories can be very convoluted, and it is difficult to apply standard machine learning and data analysis to this sorts of objects. We'll see something about that. And the last challenge I'm going to talk about is privacy. So all this data from people, their GPS coordinates, their activities, events, where they were, at what time, co-located with which other person, all these are sensitive information. And when we start designing systems based on this, particularly things like locations of people, it is extremely hard to make sure that we are not inadvertently leaking something sensitive about someone. So this whole business of learning for transport while not compromising privacy of people is extremely hard. So today we are going to talk a little bit about these topics, and we are going to discuss, well, or rather just mention some results we have on this. Clearly, these results are not sufficient. We need many more results on these, a lot more research on all these topics. So let's see. Okay, so let's start with the challenge of computation. Why is computation difficult for transportation or mobility issues? So the thing is that, let us say we have been given trajectories, which may be movements of people, which may be routes of buses, which may be routes of taxis, etc. And in this picture, we have some clusters, like we have, we have this green cluster of several taxis, perhaps, that move similarly. Similarly, we have the red cluster, the yellow cluster, etc. Now we are given, let's say, a black trajectory like this, and we ask, what is the cluster that this is similar to, or what is another trajectory that it is similar to? This is actually a very difficult question to answer computationally, because you can see that in this case, it is very similar to the yellow ones. But if it was a little lower or a little to the left, it might start looking similar to the green one, right? And so we have to compare this trajectory to many of the other trajectories. And that computation can be tricky. So the traditional method for comparing curves like this are through methods called Frechet distance, which go like this, that you have, let's say, this is one trajectory, and you have another one that goes like that. And you want to compare these two. You want to ask, are these similar? This turns out to be a very difficult question, because there are these two things, and then there is this other one. Which one is this similar to is not very easy. And the traditional method for doing this is that you would compare point by point all these various pairs of points in two trajectories, or you will compare this third trajectory with the first one. I'm sorry, it should be drawn like that. And the point being that you end up making comparison between millions or billions or trillions of points just to get an understanding of two or three trajectories. So finding a trajectory to a similar to the query trajectory will require many more comparisons, because you now have millions of such trajectories instead of two or three. So this is a difficult problem. We did make some interesting progress on this through use of something called compact sketches. So what we do is we reduce these trajectories to compact descriptions. The idea is that here, all these trajectories can have millions of points on them. our observation is that we don't really need all those millions of points. If two trajectories are similar, they will kind of hit similar neighborhoods in the city, right? So this black and yellow trajectories are similar. They kind of pass through this neighborhood. They also pass through this neighborhood, okay? So what we do is we take some random circles like you see in the picture. We take a few random circles like that, and we ask which are the circles that the two trajectories hit, okay? So the point is that here the green trajectories hit these three circles, the yellow one hits these three circles, the red one hits these two circles, okay? And turns out that the black one hits the same circles as the yellow one, so we say that the black is similar to the yellow, okay? The good thing about it is that this reduces our million point trajectories to just a few bits of information. Like you record only whether this trajectory hits this circle or not, whether it hits this circle or not, etc. And in fact, a very small number like 60 or 70 circles suffice. That means that you can compare two trajectories using 60 bits of information. The good thing about this is that it is a theoretically provable framework, meaning that we can get probabilistic guarantees of how good our results will be in finding, let's say, similar trajectories. And it is through something called locality sensitive hashes. You don't really need to understand what that is. What we described above about the 60-bit sketches is basically a form of this technique. So the way something like this would work is that you would use this extremely compact sketches to get an approximate search results of a bunch of trajectories that kind of look similar. And then you will use the full information on those candidate trajectories to get the real search result. The point is that because we now don't have to run full search on the whole data set, we first reduce it to a smaller candidate data set and then run search on that. The whole search is now hundreds of times faster. The penalty, of course, is that it includes some chances of error. So that is the first thing I wanted to say. The second thing is about complexity, which is that movements and trajectories are complex, which makes them extremely hard to compare. The previous difficulty that we had talked about was computational difficulty, but here I want to talk about something more fundamental. So machine learning, by and large, works by comparing distances between points, okay? The previous slide was about how to get good estimates of these distances, but now we are talking about what does the distance really mean. So for example, in a standard machine learning thing, you will have a bunch of points like this, and you will have a bunch of points like this. And you will say that, well, clearly this is one cluster and this is one cluster because all these points here are closer to each other than they are to the points over here. So that is your standard basic machine learning. This is easy to do when you have things in forms of points, but we have trajectories, we have movements of people, and that movement can look something like that. So two trajectories can look like this, and then another trajectory can come and look like this. Another trajectory can look like that. And then this whole thing becomes a big mess to try to compare. So for example, if I take this particular trajectory here and ask you, which one is it most similar to? Is it similar to this one here? Is it similar to this one here? It is not a very easy question to answer. Okay? This is because we no longer have things in forms of points. We have overlapping things, and then it is difficult to say what is similar to what. Once again, we don't have a concrete answer to that, but we did some research on this, and results were interesting to say. So the first result was we tried to find something called popular paths. So let's say you have a bunch of trajectories and you ask, what are the routes that are taken by many people? Like, what are the routes that are often used by taxi drivers? So if you have a bunch of trajectories like these thin lines here, what we are looking for is this blue cluster and the green cluster and the red cluster, a bunch of things that are common to many trajectories. Okay? This is computationally very tricky because there are lots of trajectories. You have to compare, once again, lots of different things. But what we found is that you can, in fact, do this very efficiently by taking some random trajectories and by taking some random points and have them act like sensors. So for example, these circles here, think of them as street crossings. We just check if trajectories pass through certain street crossings, or if something passes through near a Wi-Fi access point, and then let's say it gets recorded by that Wi-Fi access point. The interesting observation is that from a small number of trajectories and small number of sensor locations, you can actually get a very good idea of what is happening overall. This means that if we have a small sample of people participating and we can record their locations in a few neighborhoods, we can actually get a pretty good idea of what are the popular routes in a city. So this can be helpful. For example, we cannot probably get routes of everyone in the city, but as long as we are looking for popular routes, it seems a small sample suffices. We applied that to taxi routes in Edinburgh. We got data from a taxi company, and the results are this. We plotted routes used by at least 100 taxi drivers over a period of 1 month, those used by at least 70, those used by at least 30 in our sample, and we got this kind of routes that were often used with these frequencies. Kind of related to this is this question that we had earlier, that machine learning likes to compare points, whereas we have these paths which are harder to compare. We actually found a way which seems to work well in many cases by using some topological ideas. So the basic idea is very simple. The point is that all these complex motion and trajectories are due to presence of obstacles, right? So if there's a city block, there's a park, there's a lake, something that is causing you to go around it. If that was not the case, everyone would have just gone in straight lines and, you know, movement would have been very easy. So we characterize trajectories by how they move with respect to different obstacles, okay? So for example, in this case, we have this obstacle in the middle. Let me turn it to the light thing. And there's this obstacle somewhere else, okay? The way the red path goes is that it goes basically to the left of both these things. And the blue path goes to the right of the first one and to the left of the other one, okay? So it is going around this. So we can just measure the angle each of them subtends to the corresponding obstacle. So the red path here, let's say if it creates a positive angle, then the blue path creates a negative angle, and both of them create a positive angle with respect to this obstacle too. The result is that we have now transformed this into angles created with respect to different obstacles. So they are now just points in this space on the right. And if you compare there, you find that this green trajectory is very similar to the blue trajectory, okay? This angle idea is very similar to winding numbers, if you are familiar with that, but it's not very critical. I think you all get the basic intuition. The very nice thing is that we have now taken these complicated trajectories and transformed them into points like this. So we can now apply all our standard machine learning things. So we did that, and we found that it produces nice intuitive clustering of the type you would expect in these things. And you can separate out different clusters and it produces good predictive results. Yes, Caitlin, I'm aware that we are running out of time. It wouldn't take long. The other question is privacy, which is, like we said, that location is sensitive information. And the problem is that analysis of location can give away critical properties about people's behavior. Even if we don't release the data, we just release statistics or we take decisions, it can leak critical information, like a person leaves home at 9 every day, or they met with somebody at a certain place, and that kind of stuff. The problem is that it is extremely hard to hide such all individual pieces of information while retaining value in your machine learning process. And we did something with range queries on graphs. So we can ask about the number of events, like how many taxi trips were made from inside this region, or how many people took the bus that goes around this route. Okay, and we can do this with a technique called differential privacy, which gives us privacy guarantees. But of course, this is very restricted to certain types of queries, and we can't do everything with it. So to summarize, our challenges are that we are dealing with complex objects and like transportation routes or transportation networks, and machine learning on complex objects is hard. We have the problem that mining on large data sets is expensive. We have the problem of privacy, which is incidentally largely unsolved. Like many people have asked me that, okay, so what do we do about privacy of trajectories? And nobody has an answer to that, neither for actually the previous questions. And the last thing I would like to point out is that the pandemic raises its own challenges. We want social distancing. We don't want people to take lots of people together in one public transport vehicle, which is kind of contrary to our priorities earlier. So this whole thing is itself a challenge, because we have found that mobility of people is essential, like it's inherent to the spread of COVID. On the other hand, mobility is essential to our social lives. So how to maintain transportation and movements while avoiding a large-scale pandemic is, I think, a very difficult and very important question. Thank you.
Thanks very much for that, Rick. That was really interesting, and it raised lots of questions, certainly for me. I think we'll probably hold the questions to the end and be able to cover those at that time. But many thanks for that.
Thank you.
So,
trying to stop sharing. Have I stopped sharing?
nope, still seeing your screen.
I found the cursor. Now it should stop. Okay.
Always takes a minute. Okay, our next speaker is Said Mahdi. He's been having some internet connection issues today, however, so I'm actually going to be sharing his presentation in the form of a video. So he's a student at the University of Glasgow, and we'll be talking about CAVs. So hang on one second, I will share my screen and get that started. Okay, I'm having issues. I don't think the audio is playing.
Hi, Kathleen, can you hear me?
Yes.
It's Jonathan here. So just on the bottom left-hand side, there's a tick box to say share audio on the Zoom call itself.
Okay, let me just go to that.
There's a tick box
so,
for her to do the
yeah, I'm just trying to find it. Sorry.
So just under the share screen option at the bottom there.
Okay, except it's not.
what you're sharing, bottom left corner, it'll say audio.
Everyone, my name is Said Mahdi from Urban Big Data Center, University of Glasgow. Today I want to talk about...
Okay, technical difficulties. Hang on one second, and I will try to get this up and running again.
To every car journey costs around 16 billion pounds a year, or nearly 1% of GDP. And another interesting thing is that...
Okay, Patrizia, would you be willing to be our second speaker while I try to get this sorted out?
Yes, that's not a problem. That's fine.
Oh, perfect. Okay. If you can do that, then I will work to get this settled without wasting everyone's time.
Okay.
Great. Thank you so much.
Be able to see my screen now.
Yep, it's perfect.
Yes, we can, yes.
Okay. Thank you very much, Caitlin. So today we'll present you a case studies on the demand project we just completed in collaboration with the Department for Transport. And we have several examples on how to use data fusing and data mining techniques and also machine learning. This project was all about understanding the barriers and the failures in the market when we want to introduce demand responsive transport or we want to appraise mobility as a service. There is a need for the government to understand how to appraise this type of services, and at the moment there are no tools able to provide an holistic view for what is happening. As a result, most of the services are unstable. They usually last between 10 months and 1 year, and they leave the users with no alternative at all. Demand modeling is a very good tool to understand and de-risk the introduction of these services, but the transport modeling that we're using at the moment, they're quite different, and they're not able to address the challenge that we got to when we look at mobility from a broader point of view. So we had a foundation studies a couple of years ago which look at requirements, and we identify agent-based modeling as the best tool able to represent the door-to-door user journey. So when you need to provide mobility to the users, you need to be able to cater for their full mobility needs. So you can't just serve just one leg of the journey, but you need to understand their travel patterns, their mobility needs, and what they would like to see on the ground. So agent-based modeling, at least the next generation, is a very computing intensive modeling tools and heavily rely on data. So you can build two types of data landscape. One is the urban environment, where you got a very data-rich environment with lots of new data sources coming from mobile network data, other location-based data, but also Internet of Things, sensors deployed in the urban areas. And then you got the rural context that is instead perceived as an area where you only got legacy data sets. Sometimes are also outdated, so they're not fit for purpose to understand travel patterns that you currently have. And also, one of the biggest requirements that we need in order to understand demand for mobility services, we need to be able to integrate and interface with the legacy tools and being able to transferable these results to other transport modeling, which have been created for other reasons in the past. So during the demand project, we created this methodology, which allows us to create a large-scale agent-based modeling it's a urban demonstrator, which we built for the Tan and Weir. Most of the time when you go travel patterns, you soon realize that you can't model just for your area of interest, but you need to expand the model coverage up to a regional level, because rural areas and urban areas are closely connected. So the model was expanded to the entire Northeast, and we developed an agent-based modeling with activity-based approach. So instead of having a single disconnected trips, we know exactly the full activity chains of a group of people, because we use higher granular spatial and temporal granularity for mobile network data. These mobile network data have been already anonymized and aggregated at source, but it's still a data-rich approach to transport planning. We use a huge amount of readily available data through open data available from the government, from the universities, and other data centers. And we also wanted to understand the attitudes of people towards shared mobility, because whilst mobile network data gives you what is happening at the moment, so current travel patterns, you don't have an idea of suppressed demand or latent demand. So it's important to understand also the attitudes of people towards sharing. So when we create the framework, as you can see, this is pretty similar to the first step modeling. So we developed the data input for the infrastructure, the synthetic population, and the mobility services. Transport infrastructure is created in the same way. We use OpenStreetMap data, so road network, rail network, facilities data, which are settings around education, leisure, shopping, and also business centers or logistics centers. We validate the data. These are millions of records for a region. So the validation is not standard one. So we created bespoke tools in pilot to validate the network and make sure that the capacity of the network, the direction in each road was the correct one, and then imported everything in Maxim. The real innovation in an agent-based modeling for urban mobility is in the way we create the synthetic population. We move away from agent-based modeling built on households. We use instead mobile network data to generate our synthetic population, which is a large synthetic population, because all the travel patterns are coming from the mobile network data, including social demographic information. In doing so, we also created a data exploratory framework to be able to enrich the mobile network data with purpose and mode of travel. And we run a survey of residents and a stated preference survey to understand the latent demand and which are the perceived costs for shared mobility services for the residents of time and where. All this information is then again imported into the Maxim platform, creating our synthetic population. The mobility services have been created in the standard way for step modeling. So we got a public transport with route timetables, fare structure, but also vehicles. And the shared mobility can be represented as dynamic agents, either as a door-to-door service or a corner-to-corner service. As I say, the model coverage extends nationally with an higher granularity and a higher granularity of data around time and where. We acquire mobile network data, a lower super output area, still anonymized and aggregated. We don't require to know exactly where the single person is going, but we need to understand how a group of people moves around. The Northeast is at the standard granularity at middle super output area. And then we acquire local authority district data for the rest of England, and we consider Scotland and Wales as the one country to make the model less computational intensive. So we had to adapt, otherwise we were going to model national transport model. We acquired two mobile network data sets. One, the origin destination matrix, and the other one is called trip chains, which is something that Connected Places Catapult have been working with for the last for the last 5 years. So it's a data set that allows you to understand all the intermediate trips that you're doing, but in doing so, you lose purpose and mode of travel. So the methodology that we have created is looking at rebuilding this information into the activity plans table. And we also acquired social demographic information coming from the mobile network data, age, gender, and spending power, which is similar to income. So our synthetic population has been generated from mobile network data. We have divided the sample in homogeneous daily activity patterns. We have used high definition specification. So how many trips groups of people had in one day. So we go from 1 till 21 trips in one day in the Northeast, whereas one is either a not return journey, so when you don't come back, or when you arrive in the area but is not a residence, or you got 20%, for example, of these trips which are internal trips. And then we analyze every single group independently, and we build a methodology that is able to understand, reading the two data sets, what are purpose and mode of travel. For the first groups between 2 and 4, we are able to find home and work location from the origin destination matrix. These are very precise mobile network data. For all the other trips, you're not able to understand what the users are doing because the purpose in mobile network data is simply marked as other. So we use facilities data set, land use data, and the time of travel and how far they were traveling to understand the purpose of travel. So many local trips were done for leisure. Other trips, especially above 6 trips in one day, we start to see longer local distributions of goods. So usually the long distribution is between 6 and 12. And when we reach 21 trips in one day, it's actually a white one doing deliveries locally. So we have been able to see the patterns when the people were traveling, if they were using public transport, what type of public transport they're using. In the Northeast, you got the extra addition of the underground as well. So we have generated a method to recognize automatically if the public transport user was using the metro or the bus. And also we collected the information from a survey of residents and understanding what type of attitude they would like to have if a demand responsive transport services is introduced. And the Italian wheel has not been introduced yet. Mostly the respondents were not really keen to use shared mobility. This is because they never experienced. They perceive there is a discomfort, either because of the comfort being in a small vehicles with people that they don't know, so they're concerned about privacy and safety. Most of the time we found that younger generation and well-educated people are more keen and more open to use shared mobility. But when we also comparing the results with the segments that the DFT use for that, and we found that the older, less mobile car owners, so those that are always use the car and they get access to a car, when they tend to be less mobile, they would like to use shared mobility as a way to be more independent for longer. And also the town and rural heavy car use, so which are 20%, 24% in the UK. They also are quite keen to use shared mobility. So they see shared mobility as a way, a mode of transport intermediate between having their own car and use the public transport. We developed a stated preference survey as well, so we can understand from the methodological models that we developed, which are the value of time, the cost for shared mobility as well. And we tailor these coefficients for public transport and shared mobility, and we use them in the scoring function in the Maxim itself. Maxim is quite computationally intensive. This model runs in 80 hours, just for 10 iterations. This kind of model should run for 150, 300 iterations in order to reach the full stability. But because the data input has been validated and is quite punctual, we had very good results with 10 iterations already. The benefits of using agent-based model to model mobility is undoubtedly the holistic approach. We got in one platform, we can see all the interaction between private cars, public transport. We also can see the contribution of shared mobility towards this public transport ecosystem, whilst other transport models, they're not able to consider an integration between these two models. At the moment, because of the pandemic, the model is a digital twin for the time being. So we will have development to do around scenario testing and possible different type of new mobility services to test. The tools that we are generating are platform agnostic, so we can generate a synthetic population, a very large one, very rapidly, thanks to the data exploratory framework. And it's quite easy using the same type of data format to change the data format and use the tool itself. The tool is developed all in Python. We can understand the uptake of shared mobility, but we can also consider the integration with rail, aviation, and maritime that usually are not supported by other tools. As a future development, we are looking at expanding the sensitivity analysis, including other data for validation and calibration. Many of the transport models are only validated using punctual data like the ANPR camera. By using an agent-based modeling like this, you require much more data to validate such an extensive model. And of course, we need also to adapt to the transport appraisal guidance, because they don't consider at the moment a data-driven modeling like this one, which can reach an higher precision in what the model can achieve. As a next step, we are applying the same methodology to rural areas to understand how mobile network data performs in low density populated areas. We have seen already quite good results around the 3 case studies that we are developing across England. So there is a good potential to transform the methodology in rural areas. And potentially, once this is, the methodology is valid for rural areas, we can also expand this to a national transport model. But we require a lot more computation intensive. So if you're interested to know more, at the moment we are doing the dissemination of the project, and we got some papers that you can read as well. And that's it. I think I've been on time. I hope you solved the issue at the same time.
Perfect timing, and I think everything's solved at the moment. The issue
Perfect.
seems to be on my end. But thank you. That was a really interesting presentation, and again, just raised so many of the issues that we're having at the moment, the emerging opportunities that there are, and certainly the applications for that. So many thanks. I will look forward to having some questions in the discussion. Okay. All right, so I'm going to try this again. I've been told that everything should be fine. So let's try again. I've got share computer sound, share. Okay.
Hello everyone. My name is Said Mahdi
Kathleen, we can hear that audio.
from Urban Big Data Center, University of Glasgow. Today I want
Kathleen,
to talk
can you hear me?
about
We can hear that audio now. That's
CAV-based
fine. Thank you.
adaptive traffic signal control with reinforcement learning framework. About traffic lights, the Institute of Economic Affairs claims that just a 2-minute delay to every car journey costs around 16 billion pounds a year, or nearly 1% of GDP. And another interesting thing is that the number of traffic lights in England has increased by 25% since 2000, while the number of cars on road grows by just 5%. It means that traffic lights play an important role in traffic management, especially in urban area. And in this study, we try to design, implement, and evaluate a fully adaptive traffic control system in order to optimize our traffic environments. There are 2 different levels of control strategies in traffic signal control. First, intersection level, that we can control or cycle legs, and also phase split means that green share between different phases. And also in network level, we can control our offset. It means that a starting time between phase cycles at adjacent intersections. For example, here we have around 20-second offset between our 2 adjacent intersections. This is our architecture for 2-level traffic signal optimization. At first, based on traffic assignment results, we know about current traffic flow and also our first signal program. Then we try to optimize our system considering 2 levels. First, intersection level, try to optimize cycle time and split time between different green shares. And in network level, we try to optimize our offset using this new signal program. We reassign our system and we find our new traffic flows, and we continue this loop in order to optimize our system in whole network. There are three main traffic signal control approaches. First and most common is fixed time system, that we use pre-timed control based on historical traffic data, and most of the cities use this simple signal control approach. Second one, actuated system, when we use some simple logic in order to optimize our signal control. For example, extend green time for main approach until we have some vehicle in other approach. And adaptive system, when we try to adapt our traffic based on real-time traffic flows and using intelligent traffic control. We are trying to develop fully adaptive system based on our framework in this study. Here you can see an overview of traffic signal control optimization approaches based on different level of intelligent decision making. In this study, we are trying to use model-free learning adaptive control based on reinforcement learning framework. In reinforcement learning, the agent interactively observes the state of environment, takes an action accordingly, receives a feedback reward for the actions taken, and adjusts its policy until it converges to the optimal mapping from states to optimal actions that maximizes the cumulative rewards. So, for example, in traffic network environment, the agent could be signalized intersection, or, for example, trajectory planning, when we consider different connected vehicle. For example, signalized intersection can take an action, switch or phases, extend, for example, green time for one phase, or switch to another phase, and change or environment or traffic flows based on changing this phase. And we can check different performance measure, for example, queue lengths and delays, and try to optimize our signal control in using this closed loop system, taking an action and receives feedback reward from our environment. As you can see, different studies have used RL-based traffic signal control, considering different state, reward, and action policies. But in our study, we try to use RL framework in CAV environment, connected and automated vehicle environment. Let me explain a little bit about the importance of AV and CAV in traffic management. 8 Japanese researchers have conducted real-life experiments shows that how traffic jam occur for no particular reason. They placed 22 vehicles on a single track and asked the driver to cruise around at the constant speed. Simple task you would think, but you can see what happened after a few seconds. It collapsed the traffic because humans are not able to maintain distances. So other universities model this experience and try to change to connected and automatic vehicle environment. After a while, change driver behavior, and you can see now how connected and automatic vehicle can manage or traffic, and all vehicles can follow same routes, same. Existing traffic signal control systems only allocate green time to different phases to avoid congestions. Considering CAV technologies, trajectory planning not only provides more information than existing infrastructure-based detection systems, but also can be controlled to further improvement in mobility and sustainability. Green start, duration of each phase, and also cycle lengths can be optimized together with vehicle lane changing behavior or maybe vehicle arrival times for minimizing or delays or other different performance measures. We implement our idea in one single intersection using a simple three-phase signal control, as you see in this picture. We are using dynamic demand, time varying volume for different time intervals for different approaches. In fixed time CAV scenarios, connected vehicles receive the information about the time until the next green starts and next green end from the signal control, together with the current distance from the vehicle to the signal. The optimal speed for arriving at the next green start and end is calculated. In this case, our CAVs can adjust their speed based on next green start and end and minimize our total delays. Here you can see how can we use this speed guidance idea in order to arrive to the intersection at the next green start without delays. Here you can see average queue lengths, different traffic movements in our intersection. As you can see, considering CAV environment could improve our average queue lengths in different traffic movements. And also, it could improve average delay compared to other signal control scenarios in different traffic movements. This slide presents evaluation of our model. The y-axis shows our 4 signal control scenarios with different traffic environments, actuated and in conventional environments, reinforcement learning in conventional environments, reinforcement learning in CAV environments, when our controller can receive data from our CAVs as an input, and fixed time controller in CAV environments when CAV can send data as an input and also can receive data about adjusting their speed based on next green time start and end. And the x-axis presents the percentage difference in comparison to the base scenario where a fixed time and conventional environment is implemented. Different colors are used to depict different performance measures, below for average queue lengths and orange for average delays. As it can be observed, or RL scenario in conventional environment could improve our performance compared to normal actuated version, and using CAV environment could improve our performance compared to conventional environment, and using fixed time controller in CAV environment, considering a speed guidance, could improve or performance significantly. For the next step, we are working on reinforcement learning framework that in CAV environment that can consider speed guidance. So in this case, our CAV can send data to our RL controller and also can receive data about estimated next screen time start and end. And hopefully in this case we can improve our performance compared to fixed time in CAV environments. Finally, you can see very congested traffic network considering different kind of vehicles. It means that technology won't save us from a policy problem. Autonomous vehicles are still just cars that take up geometric space. If we make driving easier and cheaper, you better believe humans will do more of it. And if we aren't careful about the regularity and policy framework around the future of cars, we may end up with simple more of them. Finally, I want to sincerely thank you for your attention and welcome any questions.
All right. Let's see. Can I be heard?
Yes, we can hear you.
Great. I will give my apologies. I'm at a disadvantage at this point because while I could see the video very well, the audio was not working for me. So apologies for that. But I think I caught quite a lot of it. So if I could get our speakers to perhaps turn your videos on if you're able to, because this is really the time when it's a chance for a bit more discussion. And I think we saw from the presentations that there's a lot going on in the transport sector that deals with computing science, with data science, and really with how that has implications for what happens in the real world. So perhaps, Rick, if I could maybe start with you, and I would say for our participants, if you do have a question, go ahead and put something in the chat or in the discussion forum. Otherwise, I'm just going to talk quite a bit because I have a lot of questions. Rick, one question that I had for you, when it comes to the trajectories, you talked quite a bit about space. Do you also look at any temporal considerations around that when you make your allocations to the trajectories?
Sorry, what do you mean by allocations to the trajectories?
So when you're working on looking at clustering information or about joining them together, are you looking at temporal characteristics?
Yeah, very good question. So just clustering the trajectories in space, like you saw in my pictures, that is, someone had moved from here to here like this, and someone had moved from here to here like this, possibly at the same time, possibly at the different time. Doing this clustering versus someone had moved like this at a particular time, let's say in the morning, and someone had moved like this at a particular time in the evening. These are different questions, definitely. Doing things in 3D is usually a little more harder than doing things in 2D. So when we take time, we have a third dimension, which of course makes all the computational things harder. But I don't think it is prohibitively hard. It is just, I think, a little bit harder. The reason that we did not do the 3D analysis so much, or did not spend a lot of thought on that yet, is that I feel it depends a little bit on your application. It's a question of, okay, two people moved similarly. Do you consider them same or different if they did it at different times? This seems like a very application dependent question. So for some cases, someone doing this today at 9 o'clock and tomorrow at 9 o'clock are completely different things. If your question is who were actually doing that at actually the same time. For example, if you are considering that with respect to some event that took place, like a football match or something in the city, then that football match took place on a particular day, and that day, specific day matters. Whereas if you're trying to look at it from the point of view of how people behave in office hours, like in the rush hours, then today 9 o'clock and tomorrow 9 o'clock are perhaps the same thing, and they should be considered similar. So because of this kind of things, I wasn't sure what would be the right way to go about it. So we kind of dropped that and did it with space only. But yes, doing it with time, my feeling is that yes, it is possible, not too difficult, but we will have to look at the specific application, why we are doing it.
It's introducing complexity into something that's already quite complex, which I think we saw from Patricia's, from your presentation as well, because I think that question of time comes into it as well. So perhaps if you can talk a little bit about that. I know within an agent-based modeling, it increases the computational load even further.
So for me, if I go to two different individuals with the same travel patterns, but they're traveling at different times, it may be not the same activity, or it may be the same activity, but developed at a different time. Could be the case of a shift workers, for example. Mm-hmm. So you might have the same travel patterns, especially when it comes to local distribution or long distribution of goods. You might have an 8-hour shift, and from the mobile network data, even if I know that this group of people is behaving in the same way, the fact that they're not working at the same time, that means that they're the same type of agents, but I can't treat them at the same time because my traffic flows will be different according to the different time period. So in the agent-based model, this type of occurrence is treated as additional demand. So these are agents that are not able to influence the changing behavior of the other agents, which are actually people. They need to develop their daily travel patterns without having the possibility to change mode of transport. So I restrict them. So there are other rules built in Maxim, but when we treat them in the data supervisory framework, we don't treat them at the same time. Time of travel is actually quite important because mobile network data are very precise when it comes to the traditional on time. So when you stay at home or with the traditional commuting to work, so the peak time, AM peak and PM peak when you travel towards work. But all the other purpose of travel is pretty much marked as other. So when I look in my methodology to reassign purpose and mode of travel, we look at time of travel and how far they travel. So even if they got the same travel patterns, the purpose might be different. The mode of transport that you're using might also be different because you decide to travel in a moment, for example, where you don't have a bus service active. And this is something that you can check before creating the synthetic population. So time is time-sensitive step. And I know that Rick said data mining is very expensive and computationally intensive for any data scientist that attempts to work with these large data sets of mobile network data. Our data sets is made of 600,000 records, different combination of travel patterns. And we managed to generate, of course, there are same agents that are doing the same travel patterns at the same time. So we generated 650,000 agents. But it's a very large scale agent-based model compared to what we had in the past.
I find it so interesting, the inherent complexity that comes into working with transport and then beginning to look at all of the different data sets that we have available and the ways in which those can be used. I mean, it really does introduce just a scale of issues that we perhaps weren't used to seeing within the transport sector. So really introducing that, I think, is bringing in the need for, again, for these additional skills and for additional knowledge.
It's mainly because we don't have transport modeling tools that are able to explain the complexity of model travel patterns. We got an increased demand for autonomy, for flexibility. We've got new mobility services that are flexible in time and space. You don't have any routes. You don't have any timetables. So we need to treat them differently. So the beauty of having a software like Maxim, which is completely open source, allow us to code and change the behavior of your users, the agents, but every single steps requires tailoring in the software. So you need, for example, in Maxim, you need Java skills. You need to have a good grasp with Python, for example. It's very flexible Python to create machine learning and these data exploratory frameworks that we developed. And these tools are not really available on the market. The agent-based model itself is a new tool, and there is no standard and there's no guidance. So every organization is at the moment is creating their own bespoke model, which are not able to interface between each other. So what we are trying to do at the Catapult is being able to interface and integrate this tool with outputs that a demand model built in Maxim can have with a PTV model, for example, with Visum, or with a micro simulation tool. So it's beyond what you can have with a traditional transport model profile. In our project, we always work with data scientists, software developer, because data is data is numbers, but you need to interpret the data in the correct way as well. So the figure of the transport model is still important to explain what might be the interpretation of the data as well, not just a flow of numbers that appears. So it's very interesting, the relationship that you got between different type of skills and people working on the same model, but on different type of tasks.
Absolutely. Well, and I think the point that you made about, how, for example, autonomous vehicles coming in may shift things completely because they have different behavior. And I think that goes into Saeed's presentation. So Saeed, could you maybe talk a little bit about the differences that you saw within the when you were looking at the CAVs versus just looking at regular traffic?
In the case of application of CAVs in regular traffic, you mean?
Yeah, just the perhaps differences in behavior that you would see within the models that you're running.
At least in the case of reaction time, that's one of the main things, the difference between accelerate and accelerate between the human and machine in this case. And about desire speed, we have distribution for normal vehicle, normal driver, but in the case of, for example, AV, we can have constant, for example, 50 km/h about desire speed. And maybe in the case of, we can consider a smaller headway also in the case of AV environments. And about a standstill distance also, we can keep smaller than normal vehicles. And about react on signal immediately. In the case of AV, we can react immediately. In this case, we can we can decrease react time to 0, for example, for AVs. And it can help us in future if we increase how to say, number of AV and CAVs in our system. Maybe we can decrease number of accidents, or we can improve, or for example, signal control performance in this case.
I think just from what you were showing in your slides, and again, I'm sorry I couldn't hear them, but I was very much enjoying looking at them. I was like, oh, this is really interesting. I think one of the things that we're certainly seeing within a move towards AVs and CAVs is that we don't quite know what that integration will look like. So, there's a lot of development going on. There's a lot of excitement within the technology, but of course that has impacts and implications on our models. It also has impacts and implications in terms of, issues around things like privacy, like cybersecurity. And I think it's something that really kind of ties across the three different presentations, just in the impacts that it's going to have on the transport sector. I wonder if any of the three of you would like to respond to that, or talk a little bit about what you see as some of the emerging challenges, perhaps in that or other areas.
In the case of, for example, in the case of safety, and there's the trade-off between, for example, if you can trust to your AV and you are in vehicle, I think normally people cannot just trust the AVs. And so the main problem in this case is about how can we transfer from the normal traffic to AV or CAV environments, and do we need, for example, a specific route for AV and CAV at first, look like, for example, a BRT system, and for introduce new kind of environment to or traffic network. For example, in California, they are thinking about how can they create a specific route for some kind of CAVs and AVs. And another important thing is that relate to the responsibility of different kind of accident in this case. For example, if you have, because we have very rich literature about this kind of law problem, but if we want to introduce this kind of new emerging technology, so you will have this kind of accidents because you are in totally complex network, in traffic network, in highway, in intersection. So in this kind of accidents, what's the how can we interpret about the responsibility of the company, responsibility of the driver, or and so on. So that's really important for applying this kind of environment in real world traffic network, I think.
I'll mention something. I mentioned the RAINS project at the beginning of this, but that's a project that I'm involved with, and we've got computer scientists, myself as more of a social scientist, and lawyers on board with that. And that's very much to be able to look at these questions of things like accountability. You know, in the case that there's a crash, is it because the vehicle wasn't programmed to recognize that that was a pedestrian crossing outside of a crosswalk?
Yeah.
Was it a failure of something that happened within the system? Was it a failure of training, or was it, you know, was it poor regulation? And I think that's a huge question that's coming out.
Yes, so we at Edinburgh, we have recently started some work on this, and it is essentially the same question of responsibility and trust and blame and that kind of things. Exactly what you said. If the vehicle crashed, is it the fault of the controlling software? Is it the fault of the, you know, the learning algorithm? Is it the fault of the data that was supplied to the learning algorithm? And you can imagine that in these cars, different parts and different components like the control, the machine learning, various things would be made by different people. And so it is very difficult to determine who was at fault, what was at fault, what are the suitable regulations around it. And yeah, I think that's a whole big and very important area.
I think it is an important area, and I think it's one of the things that we've been looking into is, you know, what is the data that some of these models are trained on? And that, of course, goes back to some of the modeling expectations that we have and looking at patterns of behavior. You know, do we expect autonomous vehicles to behave specifically in accordance with a rules-based system? Or do we expect them to act in accordance with how people actually drive? So, Patrizia, I wonder if you have any thoughts on that.
At the Catapult, we had one of the innovative case from the project, the Human Drive, which looked exactly into this. Different drivers drive in different ways. You got the calm one, the more sporty styles, and the cab vehicle needs to be programmed in the way you would like. There could be a mom with a child that wants to have a smooth drive rather than a quick drive or a sporty style. There are at the moment my colleagues in the mobility technologies team that are looking into creating standards for connected autonomous vehicles and also verification of the behavior itself, what is expected from them. Do we really expecting, was something when we did the trials with the Nissan from Cranfield to up to Sunderland plant, at the beginning with some of the pods, there are some individuals that were bullying the connected autonomous vehicle because that was programmed to obey to certain rules. So people were crossing on purpose. And we had that also during the car projects with the Department for Transport around Milton Keynes. The people were bullying the pod because they were expected to stop. So there is a bit of a line that we need to draw that. And at the moment, we don't have regulation around what's the blueprint that we should create for the connected autonomous vehicles and how it should behave. From the transport modeling point of view, we are concentrating more on the optimization on the route. Mm-hmm. When somebody jump on board, where you should go, how you should select the route, and how you should perform. The first input that any autonomous vehicles got is to protect human life. But even that can create ambiguity in which human life you should protect, the one inside you or the one that is outside, the pedestrian crossing the road. So,
yes.
Still an open question. We haven't solved that yet.
It's very much an open question. And if for those of you listening in on the session, if you haven't taken a look at the moral machine out of MIT, that's a really handy thing to look at because it's got precisely those sorts of scenarios, like who's privileged in a case like this. But I think going back, I mean, I don't want to dominate the question. Again, I'm happy to take questions in the chat or through the question facilitation through the online portal. But also Rick, Saeed, and Patricia, if you all have questions or points that you'd like to raise having heard the presentations, I'd be happy to hear those because again, I see a lot of overlaps, but I know you all have different experiences and different backgrounds to mine, so I'd be happy to hear your general thoughts. And perhaps expectations. I mean, are there certain skills that you see emerging that are needed within transport where we perhaps don't always have what we need? I mean, I know, for example, we've done some work here with journey planners, and it's often difficult to sit in between that. Okay, on the one hand, you need a user interface that's good, so you need people who do work with HCI and design. You also need people who are able to pull in complex data that has spatial and temporal characteristics, as well as potentially characteristics around, user needs and ability. And at the same time, you need people who understand the transport system and the transport network, so they can look and say, okay, that is a realistic trip, or actually that's not a realistic trip. You're not going to take people completely around the city to go from here to here.
So something I would like to say is that, like you pointed out, this is a whole big area and in many senses very interdisciplinary, involving not just transport, but also some degree of social sciences, maybe computer science, maybe all this data science stuff. And what happens a lot in interdisciplinary things is that people usually do not talk to each other, but they sometimes try to come together and write a paper or proposal or something. My feeling is that if we are to make progress, we need, many more conversations so that each side at least understands something about the other side. So that there is a meaningful conversation later on, etc. The usual problem is that everybody is busy. No one has time for talking unless there is something specific at stake. So I don't know how to solve this issue, but this is something that we definitely need here.
I would agree with that. There's often a tendency to kind of forget about the need to actually integrate. I'm hearing laughter. Do you have a comment as well, Patricia? I know you've had your own experience with some of this.
I think it's around 5 years, I'm working with social scientists and data scientists and software developers and transport modelers. Where we started, my team now is well established. We are a group for a really cross-disciplinary across various teams at the Catapult. We are 10 just to develop an agent-based modeling. So it's a big project team. At the beginning, we had issues in understanding each other because each word we're using different terms. So we had problems in pointing out the same thing, because in transport modeling, you say something, in data science, they say something else. The social researcher didn't understand a clue. So when I explained the vision of the agent-based model itself, they start to understand where I was going. So the best thing is explaining the vision, have a good lead. So I don't know if I'm a good technical lead, you should ask my team, but they've been able to deliver the work successfully. The demand project that I just presented is a 1-year project, and really you spend a lot of time just collecting the data. And if you don't have good data and a good understanding of what you want to reach, you have a crap model. I can assure that. But if you get a good data, really agent-based modeling is something that is able to merge the qualitative perspective of the science, of the social science, with the hardcore data science, transport modeling sector, because we are able to build in personal preference of the agents into the model itself. It takes time, but it is possible. It's just a matter of willing, not as Rick said, writing the paper at the last minute. Never going to happen. Because you really need an integration of sorts. So when you start the project, you need the different type of skills that comes together and explain really well what you're trying to achieve. Many models, they can't fit, you don't have a one tool for all, but you need to specify exactly what's, like in our case, urban mobility, rural mobility, what we want to achieve, and then create on top of these the actual problem. And you can once we agreed with the terms, you can actually work very well and accept our differences.
I think you're being very diplomatic, but I also think that the results of the interdisciplinary work that you've been involved with really show, because there is a good set of that certainly coming out of the Catapult, not of your particular work. So I think that's a good thing to take away. Saeed, I wonder if you could talk about any experience that you've had with interdisciplinarity, particularly within your studies. I know you're looking at an area that is kind of inherently interdisciplinary.
Actually, I had the same experience because I joined one project related to computer science department, and now I'm working with people from different area. For example, we are looking about closed loop problem in different area. For example, medicine, urban management, and different part of the university. Some people came together and try to use same approach in different area. At first, I had a lot of problem. I wasted a lot of time to understand some new approach and new methodology. In the case of, for example, machine learning and RL, because as a transportation engineer, I don't have any kind of experience, you know, and also it takes a lot of time to explain different word, different keyword, and different method to some people from computer science part. And in this kind of project, you waste a lot of time at first to reach to the one, how to say, balance point between different person. So, but after that, I think you can start how to say, more useful approach, because people can help together. I can ask something, for example, about machine learning, RL, and so on, and I can ask. We have this kind of problem, for example, in transportation, in traffic signal, and so on. How can we use your approach for solving this problem? I can explain about our keyword or environment and so on. And in this case, people from computer science can help us to solve a problem, and we can help them to understand our environments. That's really important, and that was my experience. And no, I'm working with them, but at first, you know, I waste a few months just for matching some very how to say that some of the keywords are clear for me, you know, but I should explain. No, the queue length means that, you know, not just number of vehicles, for example, in one route. So it takes time, but I had a good experience.
I would perhaps caution against calling it a waste of time. I think it's exploring the opportunities, perhaps, or trying to come to terms. I mean, I think that was a really good point that was raised by both of you. That sometimes it's just understanding the terminology and being able to speak with one another. I know that's an issue that we've been having in the RAINS project, or not an issue necessarily, but we're kind of putting up a glossary of computing science to law to social science and what's understood by each one of those. So I think that's certainly a question that's emerging. So Rick, as perhaps the most computer scientist here, do you have any thoughts on that? I mean, you've done quite a bit of work looking into the data, but when it comes to translating that into action or pushing towards the interdisciplinarity.
Yeah, that is why I was suggesting this, that for example, I have done these things which to my mind are clearly useful, but for example, this kind of the converse point of what Saeed was saying, that I have something which I kind of feel is useful, but it will be helpful to be able to discuss with people, for example, with better knowledge of transportation, of exactly how it can be put to its best use. Similar with many other types of research I do, for example, around privacy and such. There are certain techniques I know, maybe there are more sophisticated techniques of privacy that I can come up with, but it will really help for me to know how transport people or social scientists look at it. And that will help us to, for example, together refine the problem better. And yeah, this is what would be nice to do, is if we can discuss more along these lines, not necessarily simply in the context of a project, but just more like a free-form discussion, that let's brainstorm together as to what it is that we know and what it is that we can do. That is something that I think would be very nice.
I did my PhD was done in Chicago, and it was called Computational Transportation Science. And it was a joint program between urban planning, computing science, and civil engineering. And when the computer scientists used to say, why would I go into transport? I used to say, it's like programming for video games, but it actually gets implemented in the real world. And they said, oh, okay, that's interesting. But I think that's part of what makes transport particularly exciting, is that, you know, whether it's us moving around or whether it's goods and services being brought to us, you know, it has an impact on the way that we live our day-to-day lives. And certainly with the emergence of intelligent mobility, we're seeing a lot of need for that to be supported through data science, through computing science. It's really quite critical at the moment. And I do think that we need to make sure that those opportunities are understood, both in terms of the research that we do, but also in the way that we're preparing, you know, and trying to bring new blood and new people into the workforce. So I think that's something that's really kind of on us to continue doing.
Definitely, yeah.
So we've just got a few minutes left. So I didn't know if there were any final questions, final thoughts. We may end a little early, which I think will be okay. Any last bits? Well, thank you all so much. Thanks to all our speakers. That was just a really interesting session, and I really greatly appreciate your willingness to take part and to answer my insane questions. We certainly enjoyed that, and thanks to everyone who sat in and listened. It was great to have you here. Enjoy the rest of the conference, and yeah, thanks so much.
Thanks, Caitlin.
Thanks.
Bye.
Bye.
Thanks.
Thank you. Thanks so much, Saeed. Sorry about the issue.
Sorry for my problem. It was unexpected problem for me. Sorry about that.
No, that's all right. I just couldn't hear. So thank you. Thanks so
Thank you.
much. Thanks.
Bye.
Bye. Okay, well, thanks to all our participants. It was very good to have you here. Hopefully you found that interesting and engaging. Hopefully it made you a bit more interested in transport, which is always what those of us in the transport field want, where we tend to be quite biased towards our topic. So with that, I'll perhaps ask if we can go ahead and end the meeting from our tech host. But again, many thanks to everyone.